This video covers Stat 454, Chapter 3, Section 3, Special Cases of Solutions to LPs. Previously, we discussed how to find the solution of an LP via graphing isoclines. So we took the constraint equations and rewrote them in a manner that they could be written as x2 as a function of x1. And we plotted those on the xy axis. These were the three constraints that we looked at last time. So if you take a look at the constraints and the inequalities, there is only one region that satisfies all three inequalities as well as the sign constraints. That's the region going from the origin, 0, 0, up to this point, down to this corner at 2060, down to this corner at 4020, down to this corner at 40, the pentagon surrounded by these 5 points is the feasible region of this LP. Then we rewrote the isocline so we could visualize it moving through the feasible region. By increasing different values of z, we can visualize the isocline moving through the feasible region, going until right here. At this point, this is the farthest that the isocline can travel while still being in the feasible region. Any farther, and the isocline exits the feasible region, and we have no solutions to the LP. So we discussed when solutions could happen, and we found that anytime a solution happens, it must happen at one of these corner points. That is the fundamental theorem of linear programming. Moving forward, though, that doesn't mean that every LP has a solution. We are going to discuss various kinds of solutions to LPs. The first example is taken from 3.3 example 4. This is going to demonstrate an infeasible LP. An infeasible LP is one where there are no points in the feasible region. In other words, there are no points that are satisfying every constraint. So to demonstrate that on this LP from example 4, I'm going to show you the overlap between these two constraints, x bigger than 30 and y bigger than 20. This is the top right corner of this graph. If there are any feasible points, they must be in this top right corner because that's where the overlap happens. But when I include this first constraint, y less than or equal to all of that, I see that the feasible region must also fall below this line. There are no points falling both below this line and above this line, so there are no feasible points for this LP. I didn't even bother plotting the objective function because I can see that no matter where I put it, the objective function can't live both in this top corner and in this bottom corner. The next example is an example of the case of multiple solutions. So I'm going to show you how this feasible region appears. Everything in red below this first line segment. This is from example 1 in 3.3. Everything in red below this line segment. Everything in blue below this line segment. So it's going to have to be in this purple region. And obviously bounded above by these axes. So it's in this region I'm marking off here, 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 and here. The shape bounded by those 4 points is the feasible region of this LP. Now I've gone in and rewritten the objective function, and we're going to view those isoclines and see what happens. Moving the isocline up, 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 higher, higher, higher. The isocline is starting to be outside of the feasible region, but not entirely. There are points still in it until I get to right here. So take a look at this isocline going from here to here, as well as this first constraint. The isocline appears to be parallel to this first constraint. So the solutions to this LP do occur at a corner. They occur at this corner, and I can't make it click, but the corner right there that we had visualized earlier, right there. The solutions to the LP occur at these two corners and every point in between. So this LP doesn't just have one solution, right there. This LP doesn't just have one solution, it has infinitely many solutions, and they live on this line segment. So you might be thinking, doesn't the fundamental theorem of linear programming say the solution must occur at a corner? And it does. The solution occurs both at the corner of 2030 and the corner of 40, and this LP in particular has an optimum value of 120. The very last special case when trying to solve LPs is the unbounded case. I'm going to show you these constraints that come about from example 5 in 3.3. Again, I've done the rewriting. I want everything bigger than x minus 1, that's this red area, as well as everything bigger than 6 minus 2x. So this will be the purple area, along with the two constraints obviously to the right of the y-axis and above the x-axis. So here is the objective function. Watch what happens as I move it to the right. It looks like no matter how far I move this objective function to the right, the piece going from the intersection with the second constraint onward will be in the feasible region. Increase, increase, increase. Increase, increase, increase. I can continue to increase the value of z, the potential objective maximum, as much as I want. Since z can increase without bound, we call the LP unbounded. A lot of students think that is sufficient to just see that there is a large region that is feasible, and that is not so. You need to actually visualize what the objective function does. See how the objective function increases without bound. That's what makes the LP unbounded. So these are the 4 total categories of potential solutions to LPs. The unique optimal solution, the infeasible LP with no solutions at all, an LP that has multiple solutions, and an LP that is unbounded. Your homework exercise for Chapter 3, Section 3 is to do 3.3 numbers 1 through 4. In order to complete those solutions, you need to create a graph of each of those situations using the usual techniques and demonstrate that which category the LP falls in. Appeal to the meaning of each of these pieces. Once we get into Chapter 4 material, we will learn the simplex method, and we will discover algebra ways of determining if an LP falls into one of these categories. This is all of the material for Chapter 3, Section 3, types of solutions to LPs.